Welcome to the first of two videos demonstrating how to conduct a factor analysis using SPSS for 4401. The example that we are using for this exercise is the SAQ file that you will find in the PSY 4401 Before You Begin section in the Datasets folder. You'll also find the details of this example in your field textbook between pages 682 and 706. As always, when we begin, I recommend that you spend a little bit of time getting familiar with your data. And the first thing that you should notice about this data file is that it is much larger and much more complex than any of the other data sets we have used in PSY 4401. That main difference here is that previous data sets have given you total scores or grouping categories, whereas here what your data set has is the actual questions of a scale. So we've got questions 1, 2, 3, all the way through to 23. And realistically, this is what a real data file looks like when you conduct your own research project. You would be using these individual questions to create your total scores and then running the analysis on your total scores. So this is very much what a real data set looks like. However, that doesn't mean that there's not some of you that are quietly freaking out by the appearance of this and a screen full of data. It's a personal preference thing, but at the moment we've got the words demonstrated that represent the response options, and if I wanted to change those, I would just hit the little arrow down if I had discovered there was an error in my data. But for some people, having a screen full of words like that is quite confusing. They work better with numbers. I personally like the words. I also personally will always have the words present when I am entering the data. But if you would prefer to convert that to numbers, it's just this little icon here, which changes between labels and numbers. It's certainly less crowded and a bit easier to take in when the words are gone. But let's dive into the variable view and find a little bit more about our data. So you can see we do have questions 1 through to 23, and the label this time is not a random label or question 1, because that would be quite uninformative. It is quite typical when doing factor analysis, particularly on a scale, to use the entire word of the entire wording of the question as the data label. That just helps as we get further into the analysis. You will see that the values have been coded for each of the questions, ranging from 1, which is strongly agree, down to 5, which is strongly disagree, and that's the same for all of these 23 items. Now, if you had been setting up this data file, you only need to define the values once, and then you can copy and paste it into all of the others. Something that's a little bit different from some of the other data sets that we've seen is that you will see here that missing has been coded as 9. Quite often missing is not coded at all, it's just the none there. But in this particular case, missing variables SPSS has been told that if there is a 9 in the answers for any of those questions, that should be considered as missing data. This is actually really good practice, and I encourage everybody to code their missing data rather than just leaving it blank, because if you leave it blank, there's always the question of did you miss that, rather than is it actually really missing data. So is it just an oversight by the researcher as they've entered their data, or was that question not completed on the questionnaire? But when you code your missing data, you need to make sure that you're not giving it a value that's possible in the survey. So here, the survey ranges from 1 to 5, so a value of 9 is certainly clear of that. Quite often people use 99, I sometimes use 99 for missing data and 98 for data that where somebody may have circled two responses to the one item. I can't use either of that, so it essentially becomes missing data, but it lets me know that that's different data than something that was just left intentionally blank. And you can see here that we're dealing with ordinal data because we're using a Likert type scale for those questions. If I come back to data view and think about sample size, the fact that this is such a small little blip on the scrolling screen makes me realise that this is probably a very, very large data set, and therefore I'm not going to try and scroll down to see what the number is. I'll find that out in our analyses. Now, as we delve in to the main analysis, we're actually going to do two types of analysis, looking at different rotations. But first of all, as always, we need to do some data screening and assumption testing. Now, in factor analysis, sample size is actually one of the assumptions that we need to consider. And the sample size that's required for factor analysis is actually quite debated. Tabitschnak and Fidel suggest that there should be at least 300 participants for any factor analysis. Allen and Bennett, who have written another excellent SPSS guide, say that there needs to be at least 100 or 5 per variable if there are more than 20 variables. So that's just like a general rule of thumb. But there is a fair amount of debate about it. And there are some studies that are published with smaller sample sizes, but they have considered the adequacy of their data before they've gone ahead to perform their analyses. You can conduct a test, and we will do this as part of our main analysis. It's called the Kaiser-Meyer-Olkin test, and it determines sampling adequacy. And again, it's just one of those things that we can do to check and say that we have considered that assumption. Another one of the assumptions, which is a design assumption, is that the data is independent. So in other words, each participant has only taken part once and has had no influence on the participation of another person. That's a design issue. We cannot actually test that just based on our data there. Getting now to things like data accuracy, missing data and normality. Now normally I would always start by doing analyse descriptors and frequencies, but considering the number of variables that we are going to be looking at and the type of test that we want to do, I'm actually just going to go straight to explore today. I have moved over all of my 23 variables previously, so that is why they are there, but I'll just quickly move them all back to demonstrate what I did, so bear with me. So essentially that's what you will find. You will find that you have a blank screen like that, so just choosing the top 23 variables. You can hold the shift key down and highlight them all, take them over. In terms of statistics, I'm actually just going to leave it at descriptives today. And in terms of plots, this is normally ticked, but I do not actually want the stem and leaf plot. I really am just interested in the histogram, and I do want the normality tests. So then I'm going to click continue and OK. We've actually asked it to do quite a bit of analysis, so it's not surprising that it's taking quite some time. Again, remember for your lab report assignment, this is the example of the syntax, so it's telling me the items that I'd requested, that I have asked for the histogram. We're looking for statistic descriptives as well, and a confidence interval of 95%. So that's the sort of details I can get from the syntax. Okay, so looking here, I can see that my sample size is actually quite large. It is 2,571 participants, and it looks as though there is absolutely no missing data in our data file. Now, if this was a real world situation, it is highly unlikely that there will be no missing data. The exception to that would be if this was an online survey and the survey had been set up that people could not progress through it unless they had answered all questions. And while that's great in ensuring data integrity, there are some ethical issues around whether participants should have to complete questions they do not wish to. So it's not as straightforward as just, this improves our methodology. If we look now at the descriptives table, these will allow us to look at the minimum and maximum for each question, and in particular we know from looking at the variable view that they should range between 1 and 5, and indeed if I look just at the first 2 questions, they certainly do. For the sake of this video, I'm not going to look at every question because that will become quite boring and tedious, but if this was your data and your output, that is what I would expect you to do. While we're looking at the descriptives, I'm also going to look at the skewness value, because normality is one of the issues that we need to examine for factor analysis. Now, Hills suggests that skewness is actually the best indicator of normality rather than a Shapiro-Wilks test, because it's highly likely, and we'll get to these later, but it is highly likely that all of our Shapiro-Wilks tests will be significant, suggesting that we have violated the assumption of normality. So remembering that we want skewness values that are close to 0. They're closer to 0 equaling, well, 0 being that there's a normal distribution. Out of those first 2, I'm not at all worried about question number 1, the skewness there, but question number 2 has a skewness value of over 1, nearly 1.5, so I'm a little bit curious about what's going on with that question. And just for the sake of this, I'll look at the 3rd question, and again, that's back to quite an acceptable level of skewness. Allen and Bennett, on the other hand, say that what we're looking for is approximately normal distributions in our variables, because factor analysis as a technique is really relatively robust for violations in normality. And so their recommendation is to look at your histograms and see what they suggest. So we'll just, using the navigation bar, because again there are so many graphs that have been generated and the tables are so long, I'll just click on the tests of normality, and you can see, just like we suspected earlier, all of the Shapiro-Wilks tests are significant, and this has more to do with our sample size rather than the fact that potentially we've got non-normal data. So now just going to the histogram for each of the items. This is the histogram for the first item, and I personally think that yes, it's certainly not normally distributed because we've got the peak at number 2 rather than number 3, but it's pretty close to normal, and I'd be very happy with that if that was my data. If we look at number 2, which was that problematic item which had a skewness of over 1, you can see quite clearly why that has happened. Here we've got a very, very skewed item. It looks like half a normal curve rather than a full normal curve. So that's not at all surprising that we've got a high skewness value there and a significant Shapiro-Wilks test for that. However, it's one item, and I'm going to go, it's not a huge deviation from normality in that it's not bimodal. We don't have another peak later on. So I would still persevere, just being aware that that is potentially a problematic item. And we'll look at the 3rd item as well, just as a comparison. And again, it's not perfectly normal, but it's not far from normal. So I would not be too unhappy with this data file. If, of course, this was your data file and you were doing this, I would expect you to be looking at each of your histograms and making decisions about each of the items. But for the sake of the video, I'm not going to do that because you guys will be very bored by the time I get through 23 histograms. One of the other assumptions of factor analysis is the assumption of linearity and that the variables are linearly related to each other. So what we could do is well, in theory, you should run scatter plots for every possible pairing of those variables and visually inspect the scatter plots for linear relationship. However, that's going to generate hundreds of scatter plots, considering that we have 23 variables and we would need to look at every possible pairing. So in this situation, the fallback position is to take a random sample of those. So you would pair randomly, a percentage of the variables and look at the scatter plots there. And if they were all indicative of linear relationships, then you could assume that linearity had been met. However, the problem we have, if you think back to our data, our variable view, is that we don't actually have scale data, and therefore we cannot actually look at scatter plots for linearity because it's ordinal data, and therefore we're going to get scatter plots that essentially look like rows of dots in a very systematically organised way. So there is actually some debate about whether you can even perform factor analysis with the ordinal or ranked data, but it is done. And what tends to happen in this situation is that the assumption for linearity gets relaxed a bit when you have ranked data, and it's relaxed because the ordinal nature of the variable precludes any firm judgment that can be made about linearity. Some people do go on and do Spearman's correlations between the variables if they wanted to, but we won't be doing that here. So the other point to make about assumption testing in factor analysis is that another thing that's very important is the correlation or the relationship that exists between variables. If your correlations are too low, then there's the problem there that your variables are not potentially related, and therefore they won't be able to cluster together to form factors. And the other issue is that they are too strongly correlated. In other words, we have multicollinearity or singularity, which is a perfect correlation of 1. We could, if we wanted to, go and run correlations. However, we will generate a correlation matrix as part of our main analysis, and so therefore I'm not going to replicate that here in this video. So that brings us to the end of the assumption testing that we need to do as part of our preparation for factor analysis.